So we're going to jump into some more examples with the related rates. And I do want to start off by saying these are difficult and they'll be challenging and a little bit weird at first, but the more that you do, you'll start to see patterns and they'll get a lot easier. A lot of the cylinder problems are all the same. A lot of the cone problems are all the same. So it's about starting to practice and recognize those patterns that you see. So one thing, like I said yesterday, I like to read it, underline, figure out what I have. And another second thing that we can do is to draw a picture. So water is leaking out, right? Out is key. It's going to be negative of a cylindrical tank at a rate. So we see the word rate of 3 cubic feet per second. So remember the word rate and the per second is telling us that this is a rate, a dV dt, dr dt, d whatever dt. And the cubic feet, right, that's going to be representing volume. So this is the dV dt here. If the radius, and just feet, there's no per time, so this is just r, is 4, at what rate, so they want to know at what rate is the depth of the water changing. Now depth, we could call it depth, but really if we draw a picture, it's going to be the dH dt, the height. All right, so if we draw a cylinder, right, we're going to have some water here. And so that water is going to be circular, and it's going to have a radius, and it's going to have a height. So, actually we can just draw this in a better color. Maybe. So we'll have a radius and we'll have a height. So those two things, that's what can be changing. Now in this case with a cylinder, the radius is going to be constant. So we just kind of realize, hey, the radius is constant. So what variables do we have? And really yesterday, I guess with this table, the variables would be radius and height. That would be technically our variables. And then the one that is constant would be the radius, in this case is constant. Now I do like to kind of say, okay, r equals 4. That's what we know, 4 feet. And then dV dt would be negative 3 feet cubed per second. Okay, and then the rates that were given, again, that was the dV dt. So that's what we have there. We already identified it was negative 3. So write an equation. Now, again, we have volume, so that's the equation we're going to use. So our equation is going to be V equals, and the volume of a cylinder is pi r squared h. Again, I'm going to provide you guys with a table that we can use, but we do want to start kind of learning some of these. So V equals pi r squared h. And so we're going to take the derivative of both sides. And the reason it's nice to know the constant is what we can do is instead of taking the derivative here, what we can actually do is anytime we have a constant, we know the radius is constant, we can plug in any constants. So that's always kind of what I do is I always plug in any constants before I take the derivative. So, and that's what we'll see that here, substitute values that represent any constant. So our V would be equal to pi times 4 squared h, which would become 16 pi h. Now, you can only plug in a constant. If the radius was changing, you cannot plug it in because it'll be a changing value. But when they're constant values, you can plug them in because remember the derivative of a constant is 0, it doesn't change. But the derivative of h is changing, so we can't, even if we knew what h was, we can't plug it in. So there's our formula that we're going to use to take the derivative of. So we have v equals 16 pi h, and we're going to take the derivative of this. So we're going to do d dt and d dt, and so then we get dv dt equals, now 16 pi is just a coefficient. It's going to just stay there. The derivative h is just 1, but then times dh dt, because we have to do that implicit. So there's our equation, and now we're going to just go ahead and substitute in. We knew that dv dt was negative 3 because it was leaking, equals 16 pi dh dt. Then we can divide both sides by 16 pi. Right, we're isolating for dh dt. And we get negative 3 over 16 pi equals dh dt. But we need to add in units. So what would be our units? Well, in this case, right, height is just going to be a single unit, like, feet, centimeters, whatever, and time, over time. So we just come back up here and we just double check, okay, they were using feet in seconds. So our units will be feet per second. And that'll be our units. Right? So that's kind of how I usually do the units, is just kind of at the end. Now, one thing, we're not going to have this chart, this table, to help us when we're doing homeworks or we're doing tests. So kind of like I said yesterday, how I would have set this up, I realize it's a related rate. I just kind of give myself 3 areas to work with. And so I would have said, okay, we know the radius is 4. We know the dV/dt is -3. And we want dH/dt. And that's kind of what I write down to help myself. And so I have V. So since I know about V, I'm going to just say V equals pi r squared h. And before I ever take the derivative, I always remember to plug in any constants. So, okay, this is a constant, so we can plug it in. And so that's pi times 4 squared h, V equals 16 pi h, right? And even though this question didn't tell us it's a constant, they didn't, a lot of times, see how they just say the radius of the tank is 4? And it's not like in this question up here that we did yesterday, it said when the radius is 4. So that's a hint that it's changing. And up here it said at the instant when the radius is 4. That's a hint that it's changing. Whereas this guy didn't use the word when. It just said if the radius is. That's a little bit of a hint that it might not be changing. But the other big thing that we just need to kind of realize is to think about the shape. Okay, if we have a cylinder and we have water leaking out of the cylinder, the only thing changing is the height of the water. The radius of the water is not going to change. It's always going to kind of maintain that circle. So kind of learning our shapes and kind of realizing when things are constant. So the big one is cylinders, the radius is usually constant. There are a couple others that we'll get to, but for now we'll kind of start there. So we have this formula, now we're going to take the derivative. So we're going to get dV/dt equals 16 pi dH/dt. And we plug in and we solve, we divide. And so this is kind of how I would have done it on a test and how I would have set up my paper, right? Because I don't have that table, that chart, right? The chart's kind of more for our notes to talk about everything. So next one, a cone has a diameter of 10 inches and a height of 15 inches. Water is being poured into the cone so that the height of the water level is changing at a rate of 1.2 inches per second at the instant when the radius of the exposed, I think there should have been exposed, a D, surface area of the water is 2 inches. At what rate is the volume of water changing? So this question's a little bit trickier, and I am actually going to, and if you want to, kind of set up another page, you can, but I'm going to do this one on a blank page just so that we can see how we would do it on a test or how we could set it up on a homework. So reading through this, and again, I realize, hey, this is a rate problem. I see the word rate, and it's a word problem like this. I'm thinking we're doing a related rate. I'm setting this up. So a cone has a diameter of 10 inches and has a height of 15 inches. Now, this is something that we just want to kind of get used to, is diameter we're really never going to use. We always want to change it over to radius. So the radius is 5, right? All of our formulas on the formula sheet, they all have radius. They don't have diameter. So we always want to just divide by 2 to get that radius. So we have the diameter was 10, the height was 15. Water is being poured into, so it's positive, the cone, so that the height of the water level is changing. Changing is a keyword, and rate is a keyword. And what's changing is the height. We want to go back and see what was that the rate for. And inches per second. The per second's another big hint that it's a rate. And just the inches is telling me that it's not volume, it's not area, but it's either the height or the radius. But we looked back and it was for the height. So dH/dt is changing. And since water is going into, it's positive. So that's 1.2. At the instant when the radius of the exposed surface area is 2 inches. So now we have a second radius, and this is why this question is a little bit weird. We have a second radius. And so I want to talk about this and kind of talk about how I do this. And so what I kind of think is the cone has a diameter of 10 and a height of 15. So if we draw a picture, and cones always have, this property, and it's kind of interesting. And so the first time you see it, it's going to be really weird, but you just have to remember, oh, the cone problem, we have to do these similar triangles. So what I actually do is when I write these, I will actually write this as, if it's the diameter of the cone, right, the height of the cone, of the overall cone, I'm going to write big diameter and big radius and big height. And then for the water, I'm going to write little r is 2. And you'll see when we draw the picture, it'll be a little easier when we kind of draw this as a picture. So if we draw this as a picture, we think there's water in here, right? And the water level is actually, in this case, increasing, right? We're pouring water into the cone. So water level is increasing, but this is going to be changing. So this height will be changing, right? Later on, the water might be up here, and we might have an even bigger height, right? So we see that that's changing. That's able to change. And then same thing with the radius, right? The little radius, that will change. When the water gets higher, we'll see a bigger radius. So that will change as well. So those two, the little r and the little rh, are both changing. We don't have those as constants. But what is kind of constant will be the overall radius, right? The cone can't change. You're not all of a sudden going to pour in water and all of a sudden the cone got bigger. That's ridiculous, right? So this big R and this big H, they're going to always be the same. So the big R is always 5 and the big H is always 15, right? The cone cannot change. It might be like a funnel, or it might be like an ice cream cone, or whatever it is, but that actual object can't change. Only the amount of water can change. And so what happens is every single cone question works the same way with this, where you can actually draw in a right triangle right here. If we look at this right triangle, the height of the right triangle is h, and the base of the right triangle is r, and then there's a hypotenuse. And we can draw in a second right triangle. I'll just use black for them, I guess. And our second right triangle is for the overall shape, where we have big R and big H. And so these are similar triangles. If you remember back to Math 1, you had the SAS, AAS, all that. You had the congruent triangles and the similar triangles. Well, what happens when you have similar triangles, and you don't have to ever write similar triangles on your homework, but I'm going to write it just for our notes. So what happens when we have similar triangles is that, if I knew that these two triangles were similar, and we had little a, little b, and this overall was big A and big B, kind of the review notes for that is you can say that, okay, big A over little a equals big B over little b, right? Or you could say little a over big A equals little b over big B. That's the same thing. So that's kind of our property about similar triangles. So what we can do here is we can do that, but instead of using big R, you can say, okay, big R over little r equals big H over little h. That's great. But we're going to plug in, because they're constants, we can plug them in. Now, you're not going to plug in the 2, right? We cannot plug in the 2 because it's not constant. But the 10 and the 5, these guys are constant, right? We said that the cone shape is not changing. I know this is a little bit weird, but the more, once you see it 2-3 times, it'll become so much easier. So what we're going to do is for the big R, we're going to put in 5 and just leave little r alone. The big H, we're going to put in 15, leave little h alone. And then we're going to go ahead and cross multiply. And so we're going to get 15h equals 5r. And so now we have a formula with an h and an r where we can actually plug these in, and that's very, very key. And so the key is that we want to remember which variable are we solving for. Are we solving for r, or are we solving for h? And so when we come up here and they said, at what rate is the volume of the water changing? So we're actually solving for the volume. So in this case, it doesn't really matter. So in this case, what I want to do is I want to basically get rid of r because I know about h. This is what we know about. So we know about h. So if we can go ahead and get rid of r, that'll make our life a lot easier. So we're going to isolate for r. So we're going to divide both sides by 5. And you're going to get 3h equals r. And so now we can plug this in for r. We can plug in 3h to a formula with r. Okay, now, could I have instead, when we had 15h equals 5r, could we have divided by 15 and gotten 1/3 r and then plugged in for h? Absolutely, that works. The only problem with that is that we knew about h, and so that's going to help us. Now, this one's actually tricky anyways because we don't know what the value of h is, so we'll kind of get there. So basically our formula in this case, in our middle case, we're going to have two formulas. Okay, our first formula is the one that we just had, which was 15h equals 5r. I'm going to write it like that. And then our other formula, I'm going to skip a few lines. Our other formula will be v equals 1/3 pi r squared h. That's the formula for a cone if you look on your table. And so what's going to happen is we see that I have two variables. I have an r squared and an h. So that would have been product rule. But I don't want to do product rule. To me, product rule just doesn't seem fun. So what I'm going to do instead is, like I said, I'm going to divide by 5 because I knew about the dh dt, and that's important to me. So that gives me 3h equals r. And so now what I can do is I can go in and I can plug in anywhere I see an r, I can plug in 3h. So this gives me volume equals 1/3 pi times 9h squared times another h, which gives me 3 pi h cubed. So this is a much better formula. And so now what I can do is I can go ahead and I can take the derivative of it. So I can say dv dt equals, and really I'm taking the derivative of this guy down there. So the 3h cubed is going to come down and make us have 9 pi h squared, but then times dh dt, right? We always need to do that implicit part. So now I can start plugging in, and we're solving for what rate is the volume changing. So we're solving for dv dt. So we know we can't plug that in. And then when we get to h, we kind of have an issue. We don't know what h is. Now, we do know that dh dt is 1.2, but we don't know what h is, but that's okay. And that's why we have this second formula back here with the 3h equals r, right? Because we did know what r was. R was 2. So what we can do is we can plug that in and say, okay, 3h equals 2. That means h has to equal 2/3. And so now we know what h is. So now we have dv dt equals 9 pi times 4/9 times 1.2. And honestly, if you don't have a calculator, I would just leave it like this. There's no point in trying to multiply out when you don't have a calculator. But you do need to have units, okay? So our units here, inches, right? But it's volume, so it's going to become inches cubed per second because they gave us second. So our answer would be dv dt equals, we can cancel out the 9s. So, oh, and this is actually not too bad. 4 times 1.2 would be 4.8. So 4.8 pi inches cubed per second. So there's that. And I know this is a trickier question, but essentially what we want to kind of remember, the process for cones are, when we have a cone, we always kind of start off with this similar triangles for cones, and we plug in the overall radius and height, and that's going to help us to get this kind of equation here where we can then have a relationship between h and r. And the reason that's important is up here when we had v equals our formula, v equals 1/3 pi r squared h, this has two variables. And so what this formula allows us to do is it allows us to take those two variables and bring it down to 1. Okay, next one is a ladder. Is 25 feet long, leaning against the wall of a house. So the ladder is 25 feet long, and it's leaning along a house. The base of the ladder is pulled away from the wall at a rate of 2 feet per second. So we know that one's a rate. So I always draw a picture on these. So I'm going to draw it kind of, here's the side of my house, here's the ground, and here's our ladder. And the reason drawing a picture helps is it kind of helps you to also visualize what's going to be constant, what's not going to change. So a 25-foot long ladder, right? So the ladder is 25 feet, and if we kind of imagine the ladder falling, it's not going to all of a sudden get longer or get shorter. So we want to always kind of write in our constants. That's very important. It's a very important thing to do. So that's a constant, and that means we can plug it in as soon as we want. And then, this side, it's a right triangle. So this side, I'm going to just call A, and this side, I'm going to call B. Now, you could have also called it, base and height, but I like A and B because A squared plus B squared equals C squared is nice and easy for us. So how fast is the top of the ladder moving down when, right, that's a keyword that something's changing, when the base of the ladder is 7 feet from the wall. So again, I'm going to kind of set this up into my 3 stages. So on my left, I know that C is 25. I'm going to just kind of add in that it's a constant. That means I can plug it in right now. Okay, the base of the ladder is pulled away from the wall at 2 feet per second. So the base is going this way. The reason this is important is when we draw the picture, that helps us to visualize, is this a positive or a negative number? And the way we know that is it getting bigger or smaller? So if we pulled it away from the wall, A is getting bigger. So since A is getting bigger, then we know that this 2 is a positive number, right? And it's the rate for the base, and we're calling our base, our variable for our base is A. Even though, you could use base and height, I'm calling it A. If you wanted to use base and height, you could call it B. But that means that this 2 in my picture matches up with dA dt, and it's positive 2 because if we pull it away, it's getting bigger. The A is getting bigger. How fast is the top of the ladder moving down, right? So if this side goes to the left, then obviously the top of the ladder is going to have to go down if you kind of just visualize it. So we want to know, we want dB dt. That's what they're asking for, and we kind of know in our head it should be a negative number. When the base of the ladder is 7 feet from the wall. Now, is that A or is that B? Well, let's look at our picture. In my picture, that's A. The base of my picture is A. So we also know that A is equal to 7. So what's our formula that we know that has A, B, and C for right triangles? That's A squared plus B squared equals C squared. Now remember, we can always plug in just the constants. So we're going to say A squared plus B squared equals 25 squared. That's something that we're allowed to do. So that's going to give us A squared plus B squared equals, I believe it's 625 when we plug that in. Yeah, 625. So this is now our formula. And once we do that, something that I like to really do right after I plug it in is take the derivative. And the reason I do that is I don't want to plug in 7 and then take the derivative from the wrong spot. You can only take the derivative when you've only plugged in constants. So this is going to give me 2a dA dt, right? If we do d dt, d dt, and d dt. So 2a dA dt plus 2b dB dt equals 0 because the derivative of 625 is 0. And that's why it's kind of important to have plugged in that constant so we get that 0. Now, if you didn't, let's pretend like you had forgotten to do this and you had done this. 2a dA dt plus 2b dB dt, you would have gotten equals 2c dC dt. And all hope wouldn't have been lost if you realized, hey, what does dC dt mean? It means the change in the actual length of the ladder. But that's not changing, it's 0. And so that's kind of why this ends up going to 0. So, hopefully we didn't do that. We don't do that on a test, but that's something that is just to be aware of. Okay, so now we can start plugging in. So 2 we can plug in, A we can plug in as 7, dA dt we can plug in as 2, then 2 we can plug in, but we don't know what B is. Now we want dB dt, so we know we're not going to plug in there. But the reason I like to plug in is it kind of tells me what else do I need to do. So what I need to do is I need to figure out what is b. Now, do I have any formula where I could plug in and figure out what b is? Yeah, we have a squared plus b squared equals 625. We have that formula that we did the derivative from. Now, the reason it was important to take the derivative first, remember, is because a wasn't a constant. But now that we've already taken the derivative, now we can plug in a just to solve for our other variables. So we can say 7 squared plus b squared equals 625. 7 squared is 49. When you subtract 49 from both sides, you get b squared equals 576. And then you're going to take the square root of 576, and you're going to get b equals 24. So we're going to put a 24 in here. So this is going to give us 2 times 7 is 14, times 2 is 28, plus 2 times 24 is 48, db dt equals 0. We're going to subtract 28 to both sides, divide, and you can simplify this, and we're going to end up getting db dt equals negative 7 over 12. And then our units, right, let's go back. We had feet per second. And the reason I know it's feet and not feet squared is because it's b, it's the length of something. Okay. Now, a really quick side note is just one of the reasons I knew it was 24 so quickly is there are some special right triangles that you may want to memorize. So whenever you have a base and like an a and a b of 3 and 4, the hypotenuse is always 5. And you can do any multiples of this. So 6 and 8, right, that's multiplied by 2, we would end up with 12. Or, you know, say 9 times 3, 12 times 3, we would get 15. So any multiple, like if they gave you a triangle that had 12 as a hypotenuse and 6 as a base, you could immediately be like, oh, that's a 3, 4, 5 triangle. So, you know, the height would be 8. So that's one of the ones to memorize. And then another one is 5, 12, and 13. And any multiples of that. So 10, 24, and 26 would work, right? That's kind of a common one that they use on the AP exam a lot is 10, 24, and 26. And there are more, but the third one that's just very common is the one that we just did right here, which is 7, 24, and 25. And so these are just kind of our special right triangles where we have whole numbers. And those are a lot more common on the AP exam, especially on the non-calculator portion. So if you can memorize those, if you remember them, those are very kind of a good thing. They're not necessary to know, but they'll just kind of help you out and make things a little faster for you. So now we're going to consider the triangle formed by the side of the house, the ladder, and the ground. Find the rate at which the area of the triangle is changing when the base of the ladder is 7 feet from the wall. So we kind of have our same givens. And actually now we even know more because we've solved for this and it's the same 7 feet. So we still know C is 25. And we know that that's a constant, which is nice to know. We still know dA dt is 2. We still know A is 7. But now because we've already done a lot of this work, we now also know B is 24. And we know dB dt is negative 7 over 12. And by the way, one thing to kind of remember is we had talked about, hey, this is going down, and we got a negative answer, so that's a good thing that we got that negative answer. That kind of confirms what we had thought. So now instead of doing a squared plus b squared equals c squared, though, they want to know about the area. So we're going to do the area. What's the area of a triangle? It's 1/2 base times height. Now in this case, my base and my height are a and b. So that's my my formula. And the issue here is we're going to have to do product rule. So we have two variables. If you don't want to do product rule, it's actually possible to not do it. You could take the a squared plus b squared equals 625, and you could solve for a. But it's going to get kind of nasty because you'll get something that looks like this. And you'll be plugging that in for a. And I'd rather do product rule than deal with that. So I'm going to just go ahead and do product rule here. Now remember, we cannot plug in a or b yet. Remember, the reason we can't plug them in is a and b are not constants. they're changing. So we can't plug them in until we've taken the derivative. Once we take the derivative, then you can plug them in. But first, we need to take the derivative. So when we take the derivative, I have two variables. So I'm going to do product rule. So we're going to get dA dt equals, now I'm going to put in 1/2 times 1, right? The derivative a is 1. dA dt, I'm taking the derivative first. Then I'm going to leave the second alone. Then now I'm going to leave the 1/2 a alone, the first term alone. And the derivative b is going to be 1 dB dt. And now we actually know everything from our previous question. So the 1/2 times dA dt we know was 2. B we know is 24. Plus 1/2. A we know is 7. And dB dt we solve for -7/12. So this is going to cancel. We're going to get 24. And then I'm going to move the minus to the front. I can cancel that out to be a 6. So minus 49/6. And, oh, that's my fault. Those don't cancel. They're both on the denominator. So we're going to multiply the two denominators. Right, the two numerators, 7 times 7 are on top. They go to 49, or -49. These are both on the bottom, so they can't cancel. Don't make that mistake. They're both on the bottom, so 2 times 12, we're multiplying across, right? Like if you kind of did that, you're multiplying all the numerators and all the denominators. 2 times 1 times 12 is 24. And so this is fine to leave as an answer. You don't have to multiply it out. This is totally fine to leave it as an answer. But if you did lollipop it, you're going to do times 24 times 24, and you're going to get 576 minus 49 over 24. And then from there, you can just kind of go ahead and simplify. And so we'll kind of end up with dA dt, which is the area, the rate that the area is changing. When we subtract this, we get 527 over 24. Those cannot simplify. And then our units, the units for area, are going to be units squared. So in this case, it was feet. So we're going to get feet squared. And then there's a dt, so per time, which was seconds. So our area is getting bigger, right? Because it's a positive number. That's important to realize. Our area is getting bigger because it's positive. Find the rate at which the angle would be formed by the wall of the house is changing when the base of the ladder is 9 feet from the wall. So this is now different. We can't reuse our numbers. So all those numbers that we had learned about, even the 2 even, is going to be changing because, oh no, the 2 will be the same. The 2 is the same. But the 7 is no longer in use. And then that means that the 24 and the -7 over 12 are not in use. We can't use any of those numbers we found. So we can really only use the numbers from the beginning. So the only numbers we knew about were C was 25, which was constant, and dA dt was 2. So we can still use those two numbers, but that's it, because now we're using something new. So I'm going to redraw our picture. Right, so 25, that's a constant. And then we have A, and then we have B. And they want the angle, this is important to realize which angle. They want the angle from the ladder and the house. So there are really three angles here, but we know that's 90, so they're never going to ask about that. So you could either have this angle down here or this second angle up there. And so the one from the ladder and the house is going to be the one on top. So that's our theta. So we're going to draw in a theta there. So this is going to have to we're going to have to recall SOHCAHTOA. And you're going to pick whether you want to use SO, CA, or TOA based on what we know about. And so what we know about is we know we're definitely going to want to use one with H because we have a constant there. So I'm going to get rid of TOA. That would be really silly to use because we have the constant 25 as the hypotenuse. And then when they gave us when the base of the ladder is 9 feet from the wall, is that our A or is that our B? So if we look at our picture, the base of the ladder in this case would be the A that I wrote in. So we know that A is 9. So we're going to want to use something that has A and has 25. And so if we kind of remember back from geometry, right, we're standing here, that's our angle. This is always the H. And then what's next to my star is the adjacent side. And what's kind of opposite from there, not touching it, is the opposite side. So we know about A and we know about 25. Now I'm not going to write A equals 9 here in the picture because it's changing. You only write constants in your picture. But the O and the H, that would be our sign. So that's the formula we're going to use. So we're going to use sine of theta equals opposite. Now the opposite in this case is A. Again, I'm not going to put in 9 because it's changing. Over, now for the hypotenuse, I can put in 25 because it's a constant. That's important. Now if you wanted to kind of start this off and do this, O over H, you can do that. If that helps you. And then just plug in, okay, we're going to plug in A because it's changing. And we're going to plug in 25. That's probably the hardest concept for students to realize is only plug in constants. Okay. Now, from here, now we can take the derivative. Once we've plugged in the constants, we always want to go ahead and take the derivative. So what I'm going to do is I'm going to go in and say, let's do d dt and d dt. The derivative of sine is cosine, but then times d theta dt, right? Because we're doing it with respect to t. Now here, this derivative looks hard. You could do quotient rule. It'd be really long, but you really don't have to. Because remember, a over 25 is the exact same thing as 1/25th a. So the derivative just becomes 1/25th. But then because of the d dt, we have to do times dA dt. Right? We have to do that implicit. So now we can go ahead and look at what can we plug in. So cosine of theta, that's a little bit weird. Cosine of theta is adjacent over hypotenuse. Okay, well, adjacent is the b side. So there's, a way you can do this, especially if you have a calculator and you could, try to solve for sine. You could plug in like the 9/25ths. You could do something like this, like sine theta equals 9 over 25, and then you do inverse sine. Don't copy this down because we're not going to do this. Inverse sine. You'd get a theta, and you'd plug that theta in. That absolutely works. But I don't like to do that. What I like to do a lot better, and is a lot easier, for me at least, is I like to kind of think, okay, well, we know that cosine of theta is the adjacent over the hypotenuse, and we know that a squared plus b squared equals c squared. So if we plug in, we get 9 squared plus b squared equals 25 squared. That's going to be 81 plus b squared equals 625. And so that's going to give us b squared equals 625 minus 81. So that's going to give us 544. And so b is just the square root of 544. And so now what we can say is, okay, cosine of theta would be adjacent is square root of 544 over 625. So that's what I'm going to plug in for cosine of theta. I'm going to plug in 544 over, square root of 544 over 625. Then d theta dt, that's what we're solving for. That's what they wanted. They wanted to know, find the rate at which the angle is changing. So they wanted d theta dt. So we're not going to plug in anything in there. And then 1/25th. And dA dt, oops, I didn't write that in my givens, but dA dt they gave us in the very initial question was 2. So now we just solve, right? D theta dt equals 2 over 25 times 625 over square root of 544. Right, we multiplied both sides by its reciprocal. So times 625 over square root 544 to cancel everything out, times 625 over square root of 544. And so this is going to give us d theta dt equals, that'll cancel out to a 25. 25 times 2 is 50, divided by square root of 544. And on an AP test, if this was free response, I would just leave my answer right there. I wouldn't even worry about doing anything else here. Okay, so, oh, I messed this up. Hopefully one or two of you guys got this. So I plugged in, for the hypotenuse, I plugged in 625. That's not the hypotenuse. The hypotenuse is just 25. So up here, a bunch of mistakes that kind of follow with that. all of those 625 numbers, they all should have been 25 numbers. So that should have been 25. That should have been 25. So times 25 over square root of 544. And so what'll happen actually, that was just a 25. So they actually just cancel out to 1. So 2 times 1 is just 2. So our answer is 2 over square root of 544. And that's our answer. For units, we do need units. The units of any angle are always radians. Okay, so we're always in radians in calculus. In physics and in some science classes, you'll be in degrees, right? We learned that in math, you have radians in degrees. In calculus, we always measure in radians. So radians per, and then the time in this case was seconds. So radians per second. If you want to write it all the way out, you can. So there's that one. I know this was a really weird question. I know this video is getting a little bit longer, but it is just, important to get this practice in. So we'll do one more. We'll try to do this one a lot quicker. So an airplane is flying at an altitude of 5 miles. So we have an airplane. I like to draw the picture. My pictures are always really, really amazing. My airplane is just a nice little box. So an airplane is flying at an altitude of 5 miles per hour. Or sorry, 5 miles. So in my picture, if I draw the ground, right, the height of this airplane is at 5, but I'm just going to put an H. I'm not going to plug anything in yet. Okay, let's kind of figure out what the constants are first. So, and it passes directly over an antenna. So we have some kind of antenna right there. When the plane is 10 miles past the antenna, so if it's flying to the left, it might be flying to the right. I'm going to draw mine flying to the left. But if yours was flying the other way, that's fine too. So it's flying over here. So when it's 10 miles past the antenna, so we're going to just call this, A. Maybe we'll even just call this B for A and B. So we'll have A and B because we're going to see that it's going to become a right triangle. So when the plane is 10 miles past the antenna, the rate at which the distance between the antenna and the plane, so the distance between the antenna and the plane, that's going to be our C. And so in this case, if we're kind of thinking of the plane, what's changing? As the plane keeps flying to the left, what's changing is the A is changing and the C is changing. So the constant in this case is actually the B. So in this case, this is our constant, and so we can plug this one in. This is the only one we want to plug in to the picture. So this is going to be 5. A, we're not going to plug into the picture. C, we're not going to plug into the picture because they're both changing. So we can kind of say here, now, we do know that they gave us the 10 miles past, and that is A. So we can do that as a given, but we just want to make sure that we know it's changing. Then B is 5. That's our constant, so we can plug that one in. C, we don't know, but they did give us the distance between the plane and the antenna. That's going to be the C, but that's in miles per hour, and they use the word changing. So that's a rate. So that's dc dt. Now, is that getting bigger or smaller? Well, we can kind of imagine as this guy goes out, that's getting bigger. So it's positive 240. So those are our givens. Now, what do we want? We want to know what is the speed of the plane. That's a really mean question. But essentially, the speed of the plane, speed is a rate. And the only other rate we have here would be dA dt, right? We don't have dB dt because dB dt is going to be 0. The reason why dB dt is 0 is because, remember, this is a constant, so it's not changing. So we want to know dA dt. So what's our formula? It's going to be a squared plus b squared equals c squared. Now, before I take the derivative, I'm going to plug in any constants. A squared plus 5 squared equals c squared. A squared plus 25 equals c squared. So that's the formula that we have. Now we can take the derivative of that guy. So we're going to get 2a dA dt plus 0 equals 2c dc dt. Right, that's what happens when we do dt dt to each guy. We need to remember that implicit, the times dA dt times dc dt. Now we can go ahead and start plugging in. 2 times for a, we're going to get 10. For dA dt, we don't know that. That's what we want. So actually, I'm not even going to worry about trying to plug something in because that's what we're trying to solve for. Equals 2. Now, C we don't know. and dc dt we know is 240. So this kind of helps me, I plug in to kind of help me realize, hey, what is it that I need to do next? So next we need to solve for c. Where can we solve for c? We can solve for c back in our equation. A squared plus 25 equals c squared. So 10 squared plus 25 equals c squared. So that's 100 plus 25, or 125, equals c squared. Take the square root, and we get square root of 125 equals c. So square root of 125. So it's going to give us dA dt, 20 dA dt, equals 480 square root 125. Divide by 20, and we get dA dt equals, the zeros cancel out, we get 24 square root of 125, and we need units here. So our units are going to be miles per hour, right? The distances were in miles, the times were in hours. And then we're going to just kind of almost redo the same two questions we had before. So the radius, some of the questions we've done earlier. The radius of a sphere, this was from yesterday's notes, is increasing at a rate of 2 inches per minute. So again, drawing a picture really, really helps on these. So we're going to draw in our radius. Now this is increasing. So if the sphere is increasing, then, and if you want to kind of draw it 3D, you can. If this is increasing, the radius is going to be changing as well. And so the sphere, the radius is increasing. So what is increasing is the radius. So we know that that's going to be dr dt equals 2. Find the rate of change of the surface area. So we want d area dt, or if you want to put like surface area dt, you can, when the radius is 6 inches. So this is not a constant. We can't plug it in, right? It's changing. It's not a constant. Now, what's our formula for surface area? Surface area is, we look on our chart, 4 pi r squared. So we're going to immediately just go in and take the derivative of this guy. So d surface area dt equals 8 pi r dr dt, right? We need to remember to multiply by the dr dt. So now, our d surface area dt, or if you just want to put a, normally I'll just put a, is 8 pi, r is 6, and dr dt is 2. Very easy question. D surface area dt equals 48 times 2 will be 96 pi. Now we need the units. We have inches, but we're in area, so it's going to be inches squared. And then it was per minute. This is much more of a multiple choice question on the AP exam, whereas maybe one of these triangle questions, something like this guy, maybe the cone question that we did, those are more along the lines of free response. They take more time. Whereas the circle question would be a very, very common multiple choice question. Okay, a spherical balloon, same concept, is expanding at a rate of 60 cubic inches per second. So when we see the word cubic, we want to immediately think to volume. And the per second and the word rate tells us that it was a dV dt. Now, is it going up or is it going down? It says it's expanding, so it's going to be positive. So again, if we draw our picture, right, we have a balloon, so it's a sphere, and we have a radius, so there's no constant here. No constant. Now, this question is a little trickier. How fast is the surface area of the balloon expanding when the radius of the balloon is 4? So they're going to give us radius is 4, but we want d surface area dt. So there's a long way to do this and there's a short way to do this. I'm going to do the long way first, and then I'll kind of show you guys a shortcut. So the v is equal to, for a balloon or a sphere, is 4/3 pi r cubed. And so that's one formula. Our other formula is going to be the area formula, which is the same one we had up above, 4 pi r squared. So we can come over here and we can say, okay, this means dv dt equals, now when we take the derivative, the 3's cancel out, 4 pi r squared, and then we have dr dt. So they gave us that, and now that we've done the derivative, we can plug in and we can start solving. If you want to do both derivatives at the same time, you can, but I'm going to do them one at a time. So dv dt they gave us was 60 pi equals 4 pi. Now for r squared, we can plug that in. And we don't know dr dt, but we're actually going to be solving for it. And the reason I know I'm solving for it is kind of because I cheated and I know what's going to happen in this problem. But if we took this dA dt, because that's what we want anyways, right? We would have gotten 8 pi r dr dt. And so when we try to plug in here, right, we realize we can plug in for r, but we can't plug in for dr dt. And we need to because we want to solve for dA dt. So that's kind of why we're using the volume, and that's why they gave us the volume, is so you could find dr dt. So the pi's will cancel out. So we're going to get 60 equals 16 times 4 is 64 dr dt. We can divide both sides by 64. 60 over 64 will simplify to 15 over 16 equals dr dt. And so now that we have that, we can plug this guy in here. So those can cancel out to 2, and that can cancel out to another 2. And so we're going to get dA dt equals 30 pi, and we need our units. So the units of area are units squared. In this case, we have inches. So inches squared per, and in this case, the time was per second. And so that's how those work. So I know this was a lot, but it's really about seeing patterns. And so kind of looking at this setup, writing out your formulas, writing out all your givens, writing out all your formulas, plugging in any constants first, and then taking the derivatives. And if you stick to that pattern, and then once you take the derivatives, you plug in, and then anything that you don't know, you go back to your other formulas and try to solve for. They are tricky. They're one of the probably most difficult concepts in all of AP Calculus. So if you're like, hey, Mr. Uhart, I just don't get this, it's okay. Most people don't the first few times they do these questions, but you just do them more and more and more. You start to see the pattern. We'll practice them again before the AP exam, and you'll get better. The good news is after this chapter, some of the calculus gets a little bit easier again. This is probably the most complicated topic to understand the whole year.